he agreed, and we started reverse engineering that and to see how the process would work. From there, in tandem, he started working on Rally Bike. And Rally Bike is the first game in that hardware. It uses all the same components that I've talked about before, but it has a sprite controller. It's called an SCU, and it's another Toaplan custom. It's actually a Taito custom. They paid them to design it for their hardware. And with that, it just controls the sprites. It uses generic stuff for the tile layers. And so that was pretty much Toaplan 1. So when we got all that working over the summer of 2023, we had finished out Toaplan 1. In the interim, I had been working on Toaplan 2 by myself based on work that Pramod had done with Rising. He had made Bat Rider, Battle Back Raid, and Battle Garega. And there's also Sorcerer Striker and Kingdom Grand Prix, which we worked on together later on, but those two games weren't initially what he was focused on. And he'd given me his source code, and he had wrote the GP9001 visual display processor, which was essentially like a GPU of graphics, does everything for the graphics. So that existed. So I took previously made modules and I filled out the addressing, mapped everything, created chip selects, wired them up in glue logic, how they would work on the board, and we had Truxton 2 booting, and then I went from there and I made Snow Brothers 2 in the summer of 2022. And then about 6 months later, I sat down and I looked at Whoopee, and it had a little bit of a different architecture. It used a Z180 as well. It had a secondary CPU, and it used a different sound chip than the other two games did that I had previously done, which was OPL2. So I had to get that mapped in, and OPL2 was very difficult on that PCB. It took Pramod, myself, and Darren roughly about 2 months to figure out how to have audio output from that. And recently, I just sat down and in March, I sat down and I did Techie Pocky, which is a puzzle game, and that uses a Z180, but I was able to bypass that and just use the Z80 core that exists, because the chip that they used, all it had was an internal ROM, and that's why sound didn't exist in MAME until about 2018, because they had to decap it and extract the ROM. And so I added an additional memory stack to the Z80 to hold that internal ROM, and sound came. And we actually discovered that with Fireshark and Vimana, and so I've got Techie Pocky done. I'm working on Gox. It actually uses the Z180 fully. It has additional addressing on the chip, and it actually uses the Z180 architecture fully, and goes outside of what a Z80 uses in memory. So I would venture to say probably in a few weeks I should have it fully booting. I've got it communicating right now. I just got to get the two CPUs to talk together with shared memory. The game I want to talk about the most is Twin Cobra. Recently, within like the last 6 days, we finally got this fully playable. So we started working on it about 9 months ago. Took about 4 weeks to get it booting. We pieced together all the hardware, the 68K, Z80, the shared memory, all of that, and it uses that TMS 32010 that previously didn't exist, and a developer in South Korea named Seho Kim, also known as Rocky on the internet, who has released 2 cores for Mr. himself, makes individual modules, and it had never been proven. So he reached out to us recently and asked, if he could take a look, because we'd let him know that there were some issues. And he did, and 12 hours later, he got back to me and he fixed the chip, essentially, and addressed the shift registers, the ALU, the ALUA, the timing, and added some additional instructions. And so we were able to finish with Twin Cobra. The reason I couldn't do it beforehand was because that chip specifically controls the helicopter. And so since it wasn't reading the proper instructions, the helicopter blew up every 3 seconds, even in attract mode, which normally doesn't die. A ship doesn't die until it's supposed to enter attract mode. So it was something that we couldn't debug, and we didn't write it. He did, and he was kind enough to do it. So Twin Cobra is essentially laid out, and These are the components that it uses, like on the last screen that I showed the slide. So we've got the CPUs. It uses this Motorola 6800 and then a Z80 for sound and inputs. It also has the GLX02, which is the sprite counter, and then it has the SCU, which is the sprite controller, which was previously done in Rally Bike. It uses a YM3812 OPL2, and then it uses a Motorola MC6845. Now that's a CRTC controller. It's a cathode ray tube controller, and essentially what that does is control video timing. So it's not really a CPU, but it gives instructions and controls video, and it does 8-bit addressing. And that's the other thing that ties in with that TMS 32010. So between those two, without them, video wouldn't exist. The only difference is that controller by Motorola is very simple to implement. So once we got all of that pieced out, you build everything up and you connect everything, and then you generate the RAM for it. So there's a tile buffer, a sprite buffer, and it's just a line-based buffer to draw each line. And then there's a text RAM because there's a text graphic. There's tile RAM for the tiles, which are controlled by graphics, display, and output. And then the sprite RAM, which is tied into the GLX02 and the SCU chip. And then there's main RAM, which is for the 6800, which is the main CPU executing the code. The Z80 executes the additional code for sound and controls, dips, and it's shared between the two. So you have to create shared RAM where they can talk to each other back and forth and read addresses. And the 68K tells the Z80, I'm looking for X. The 68K says that. The Z80 picks it up in this shared memory and sends back a 1, a 0, whatever it's looking for to say, go ahead and execute this next instruction in the code block. So from those components, one of the things I wanted to talk about was Flying Shark. So Flying Shark and Twin Cobra are the same hardware. They are designed slightly different in controls, and I'm currently working on Flying Shark, but one of the things that's going on is so this is a schematic of all the I/O on that board. So it'll show how everything works. You've got up in the left, you'll see your service area where you have like tilt, coin up, and your player start buttons, and it's a 74 series logic chip. I can't see, I'm getting old. And it runs through, and the same thing with player 1 and player 2 action buttons. And so the other thing that it does is it's tied to VBlank, unlike Twin Cobra. So when you coin up, it flashes the screen. So I need to implement some logic for that, and hopefully we'll have that going sometime next week. Had to take a little bit of a break for this. And these are some of the tools that we use. So I'll reference MAME, I'll reference Final Burn Neo, I'll reference the hardware. I own this board and Twin Cobra. I'll trace them back. I'll use schematics if they exist. If they don't, and I need a specific piece of information, I'll trace it back and draw it, but very rarely does that need to occur. So from here, I'm just gonna show Twin Cobra's track mode on Mister. It's fully playable now. I just need to finish up Flying Shark and hopefully get it out here in the next week or so. So I'm gonna switch over to input 2. So the flashing comes from that CRTC controller. You can see there's a foreground, a background tile. Then you have text, which would be your game over. And then there's sprites, which are controlled by that controller. And it all ties together. It's pretty interesting. It's fun to stand these up. I get more enjoyment out of starting something out and working with Darren, our promoter, or even by myself, and seeing it grow until it's playable in the state that it would be on a PCB. And it's very exciting. Sometimes it's very challenging. Sometimes it's 3 days. Sometimes it's 3 months. Sometimes it's a year. It can take some time to hunt bugs, and it might be the smallest thing. For instance, Techie Pocky, I had to change 2 characters, and I had started working on that in December of 2022, and just now recently released it. I had to go through 1,000 lines of code and find that I needed an equal sign that was missing, and that kind of fixed most of my problems. So that's an overview of Toaplan. I'm going to go ahead and turn it over to Pramod and let him talk a little bit about Midway. We're going to switch back to input one.
Yep. That's 4. 4 and 1. Fully. That's 3. Is that okay? Oh, it's 3. So both of them need to be 1. Oh, okay. Wonderful. All right, guys. So I'm going to do kind of an overview of the Midway system that I've been working on probably for the past year or so. This is a pretty big core. I mean, I've been working on it probably since early last year, probably late the year before, and I'm still kind of working on it. But originally, I knew the requirements for the boards would be pretty advanced. It's quite a heavy system. There's a lot of things going around, especially the CPU. So initially, I intended to make this core for the Mars board originally. And so I started doing that. But then I had to use other development hardware along the way, just to kind of stand things up, see where I'm at, see how it runs on the FPGA. And so I've explored this platform on several different types of hardware, including Mister. And now I've started doing it on the Analog Pocket as well. And I've run into lots of technical limitations, which I'm going to talk about in a minute. But to give you a start, hit the wrong button. Okay, so I'll give you a background of some of the boards on the Midway series. So there's several types of boards in the Midway series. The first was the Z unit. So the Z unit was introduced in 1988. It was only used for one game, Narc. So Narc is, if you've never played it, it's a big budget game. It's a side-scrolling game where you go from left to right and you either blow up drug dealers or you can arrest them and you get more points for that. So that's a big budget game. And so the requirements of the Z unit are actually higher than all the other units for some reason or another. They just wanted to go big on this. And so this game actually required a medium resolution monitor, which I'm not sure if you've ever heard about in arcades. But that's a monitor that does 24 kilohertz, okay? As opposed to 15 kilohertz that's done, in your usual 240p stuff that you might see out there. So the requirements are quite high. The resolution is higher than the other ones. And so that was in 1988. In 1990, there's another revision of the Midway board called the Y unit. The Y unit had several games. It had Smash TV, for example, Terminator. You guys have played that. It's not a light gun game. It's kind of like a light gun game, but it's not a light gun game. Okay, and they had Mortal Kombat on that as well. In addition to a couple of other titles, I think they had like a football game. They had Trog. There's a couple of other titles on there. The interesting thing about the Y unit is they took a look at the Z unit. And the Z unit is a pretty powerful thing. It requires very specialized memory chips to make it work. And so the requirements were too high, and then it becomes like not practical to really like roll that out and produce those components and put together the board. Then on top of that, the arcade operator has to get yet another different type of monitor to actually put it in their game center. So that wasn't really practical. So they switched down to 15 kilohertz, which is the standard. Was standard at the time. It's pretty much standard overall for the period. So that's 410 by 256, roughly. Some of the games have more lines, slightly more lines, but generally it's around 410, 400 by 256, 259 vertical. And then after that, you had the T unit. The T unit had yet some more popular games like NBA Jam. I'm sure most of you have heard of NBA Jam. Mortal Kombat 2. Mortal Kombat 1 was also ported to the T unit, primarily because the end of the Y unit ended in 1992. And so in 1993, Mortal Kombat 1 was still very popular in the arcades. And so they said, okay, let's port this to the new board, the new T unit board, and let's roll it out there. It would make it less expensive than producing 2 different series boards, right? So then there's those. And then finally, the Wolf unit, which was introduced in 1995, had Mortal Kombat 3. And you also had WrestleMania, the arcade game as well. And they had Ultimate Mortal Kombat 3 and so on. Most of it is really just the same underlying hardware with slight revisions to the schemes, like the memory, higher amounts of memory, higher amounts of ROM space that are introduced on the board. So next I'm going to talk about some of the components that are involved in the Z unit more specifically. Now, in the past few weeks, what I've done is basically redid pretty much the entire core from scratch. Sometimes I do that primarily because when I take a look at something and something is very complex, I feel like I feel like there's more efficiency that can be gained, I usually start over. I know it seems counterintuitive, but a lot of the time I find it's better to do that than to kind of mess around with what's there and kind of massage it into what it's supposed to be. Okay, these are the components that I have up on the screen for the Z unit system. As you can see, there's a lot of different types of memories. There's color RAM, palette RAM, bitmap RAM. Well, palette RAM and bitmap RAM go together. Then there's main RAM, which the CPU uses for storage space to do computations and stuff. And then there is CMOS RAM as well. And you also have several types of chips on the system as well. So you have a DMA chip. The DMA is a custom graphics chip. Now, the TMS 3410 CPU also has a GPU as well. It also does graphics, but they didn't use that. And the reason why they didn't use it is because the input and output bus to the CPU is only 16 bits. In order to generate the high-res graphics on the screen, they needed a 32-bit bus output. And so they used this chip called the DMA chip, which is also called they also made another revision of it called the DMA2 chip, which appears in the T unit. Okay, so the 3410 is primarily used for CPU type of things like computations, mathematics, moving data from point A to point B, checking stuff. Primarily it's used for that. If there's any graphics to be drawn on the screen, that's going to use the DMA chip. So the CPU will actually send a command externally to the DMA chip. And then the DMA chip will send what's called an interrupt back to the CPU when it's done. Okay, and that means that the graphics were drawn, the bitmap graphics were drawn. Now, talking about the sound hardware a little bit, you had the YM2151, and then there is another thing called the HC 55564 CVSD chip, which does speech. So what's interesting is the Z unit actually has one CPU just for the music, and the other CPU does speech. So there are 2 different CPUs that work in tandem. The Y unit also has both capabilities. It also has a separate soundboard that has the same hardware. However, they consolidated it into one CPU. So instead of using the 6809 in the Y unit, they use a Z80, okay, to do both. And they can certainly do that. So there's 2 CPUs. There's one called the 6809 Master and the 6809 Slave. There's a TMS 3410 CPU, which is a large CPU. And then you have a couple of sound chips. And then you have the DMA chip, and then all the RAMs that are involved. Okay, so I'm going to take a look next, show you the block diagram for the CPU. And you can see here, there is quite a lot going on in the CPU. The CPU pretty much does everything, or it can do everything. It can generate video. It can generate your timings for your video signals externally if you want to use external video processing. It acts as a memory controller. So there's actually memory controllers inside of the CPU that you can just hook up memory chips to it, and it will just work. I mean, if it's compliant with it. And then there is a GPU that you see at the very top of the screen, and then there's a host graphics interface. Now, most of this I have implemented except for the host control. The host control that you see at the very top left of the block diagram is primarily used when you use a TMS 3410 CPU along with a secondary CPU like a 68K, okay? And I'm not targeting any of those games, so I didn't implement that. Okay, all right, so let's go on to the next one, which is the CPU block diagram. So more specifically, this is just the CPU portion, okay? So you have several different components, and the most interesting part about this is that since the CPU has several different types of blocks in which the functionality is encompassed, there's different components to it, and it becomes a very large CPU, really. This is, like the whole core will take up about 94% of the logical element space in the FPGA. So it's a pretty large core. And the most interesting part about all this is the microcontrol ROM that you see on the right-hand side. So initially, not all of this was done using wires and transistors and all those sorts of types of analog elements inside the chip. They used metaprogramming to control and extend the functionality of the CPU, and that's what's called the microcontrol ROM. So that basically is a way to extend the functionality of your CPU by implementing primitives. So let's suppose you implement add, subtract, multiply, and divide. Let's say you have those basic things. Now, if you chain those together, you can do different things, right? So instead of implementing the circuits of the chaining of all these different things together, you have something called a microcontrol ROM, which is a metaprogramming method that's used to chain all these things together as sequences of steps and then output a result. Okay, so that's what's interesting about that. And in the core, I actually had to write a microcontrol engine that would allow me to do that, because the first design of the CPU, I went through several designs, and now I'm on the third. So I'm rewriting the whole thing from scratch for a third time. In my second iteration, in the first iteration, I wrote everything in Verilog, so everything is literally wires and circuits, right? In the second iteration, I introduced a microcontrol engine, which allowed me to use RAM as a source for chaining together the instructions and these different sorts of operations without using logical space. So it allows me to save space to fit it on. And now I'm in the third iteration, which introduces more flexible types of memory controllers, because based on the platforms that I'm targeting, I want to make sure this is flexible enough to be adapted to different types of memories that are out there, QDR or SD-RAM or block RAM, something else, PS RAM, static RAM, like all these different types of memories on these different FPGA units. So in my third revision, I also cleaned up all the code and made things even smaller than I could. Next I'm going to talk about the process of I'll give you a short overview of the core implementation process, because I'm sure that a lot of you are interested in how we go about doing things, right? So the first thing we do, as Eric told you, we start from the real boards, right? We have all the real boards, and we try to take a look at the board and try to kind of come up with a high-level architecture of it. Try to get a sense as to how the systems work, what sorts of components there are, how they interact with each other. Those are some of the things that we do, in terms of surveying and figuring things out. Once we have a good idea of what components there are on the board, then we get into figuring out, okay, what's out there? What modules are out there that we can use, right? Or what do we have to create, right? And so we do that, and then once we get done with the surveying process, we figure out, okay, we have these modules, and then we have these components we need to write, and then we just get down to work and actually write those individual components, make sure all the individual components are tested very well and they work well. So for example, in this case, You have to implement a CPU. Okay, you have to figure out how to test the CPU. How do you validate that, right? And then you have to figure out, okay, there's this soundboard. How do we figure out how to construct the soundboard? Let's put that together, let's test it. And then finally, at the end, we write the glue logic for the whole system and put everything together. So once the individual components work, the whole system should be constructed and it'll work as well. In this core, obviously, doing this, there's lots of challenges, right? What I have listed on the screen are 4 distinct challenges that are very unique to this core. There's memory I/O. There's logic space, which I talked about, right? It's fitting the whole CPU in one FPGA. It takes a lot of work. There's bandwidth, right? Like I mentioned, there is a 16-bit data bus coming in and out of the CPU. And also, like, if you take a look at the DMA chip, that's 32 bits, right? So all these things and the way that they kind of push pixels to the screen need lots of bandwidth from a memory perspective, right? And then there's storage, right? How are you going to fit all those memories in the FPGA, right? You're not going to. I mean, there's no way you can use block RAM for all of it because it just doesn't fit, right? So you have to figure out, all right, can I use SD-RAM for some of it? Can I use SRAM for some of it? You know, we have to take a look and see what are the different options that we have to fit these memories because they're very needed in the system. What I want to show you is actually the Mr. memory model. Okay, this is my allocation of how I've laid out the memories using the resources in the Mr. when I did this last year. I had dual RAMs. So I had an SD-RAM. I had two SD-RAMs, so it's dual RAM. And basically what I put in the SD-RAMs are bitmap RAM and palette RAM, half of it roughly. So you get 512 kilobytes that you have to use for the VRAM altogether. VRAM is a combination of bitmap RAM and palette RAM. Palette RAM is 8 bits of a pixel. Bitmap RAM is the other lower 8 bits of a pixel. So basically you have a palette ID and a pixel value that goes with that palette ID, which is an entry in the palette. And then once you look that up in color RAM, something called color RAM, then you figure out what is the color that I need to put on the screen for that pixel. Okay, that's how that works. Okay, and in SD-RAM, I also put the program ROMs and the bitmap ROM. So the ROM is where the bitmap graphics are. So we have to take the data from the SD-RAM, figure out what pixels we need to draw. We have to process those and put them in bitmap RAM and palette RAM to push a pixel to the screen. And in BRAM, I had main RAM because the Mr. has a more powerful Cyclone 5 FPGA, so I have more space to use it for main RAM. And then I also had half of the half of the bitmap and palette RAM, and I also had color RAM in the BRAM as well. And then there's another thing called CMOS RAM, which is the settings for the board. So the configuration settings, what normally you would call dip switches, right? There are dip switches, but they're just not used really for anything meaningful. Everything is in a configuration menu that you load up, and you have CMOS RAM that saves that. So when you shut down the board, power it off, power it back on, it loads it from that. It's a non-volatile type of RAM. Okay. Okay. So I want to show you actually something. Yeah, let's go to the video, hopefully. Hopefully it works. It's on the desktop.
Yep, I gotta just stop.
Oh, you got it in some presenter mode?
Yep.
All right. Oh, no, we don't need audio.
Yeah, we don't need audio.
We don't need audio. Oh, you got to X out of that. Yep. Oh boy. Yeah. Let's put up that video. This is a video I posted last year. Okay, of this screen running on the Mister. So the reason why I'm showing you this screen is to show you how slow it is on the Mister. So you see, like, this is going going at a snail's pace right now, right? Forget about the bugs and the issues going on with this screen. But this screen is a very, very challenging screen to work on because this doesn't actually use DMA at all. It uses the raw CPU power and pixel transfers to work, right? So you can see it's very slowly moving along. So the reason why it's slow is because half of the memory for the video RAM is actually too much to fit in block RAM. So I use half of the block RAM to use half of the memory, and then the other half was in SD-RAM, as I showed you in the diagram. So it basically runs at the latency of SD-RAM, right? So SD-RAM is pretty slow in the Mister. So this screen draws very slowly. This is obviously not the real speed, and it's chugging along. But the way this is done, this spray paint effect, is basically for every line that's scrolled, basically 2 lines are copied in the background, and 2 lines are pushed in. So for every pixel that's drawn, you're basically taking 2 lines and backing them up, and then drawing 2 lines, pushing the other 2 lines back in. So you're basically reading 2 lines of 512 pixels, and then writing 2 lines of 512 pixels every single time you scroll 1 line. So it's pretty intensive. And now it speeds up because it's all done, right? Right. So that's pretty much the challenge in the Mister, is kind of getting the memory going on the unit. Now, let's see where we're at. So, okay, so that's the Mister memory model. So I tried my best. I actually worked on this for like just this problem. I've worked like 6 months on it, right? Because I tried to figure out, is there a way I can get this to work, right? Is there a way? Is there an optimization that I can do? And I tried like every single possible thing to get this to work. It would just not work. I mean, it's just too slow. It's not, the bandwidth is not enough. SD-RAM is just not fast enough in the Mister due to the way the architecture is. So there's a lot of limitations with the D10 Nano board and that sort of thing. So as of recently, I started working on the Analog Pocket. Now the Analog Pocket is better from a memory perspective. And the reason why that is because there's different types of memory that's on the board that all are operated independently. So they're not all connected through one I/O. There's separate pipes to each one of these. And so you have, in SRAM, they have something called SRAM on the Analog Pocket, and I have palette RAM there. And in pseudo-static RAM, I have, or PSRAM they call it, I have CMOS RAM and main RAM. In BRAM, I have color RAM and bitmap RAM. So bitmap RAM is the lower half of a pixel. Palette RAM is the upper half of a pixel, right? So this is actually very close to the real architecture of the board. Because on the real board, they're separated out and the writes are done independently to bitmap RAM and palette RAM. So this is actually closer to the real architecture of the board, the Z-Unit board. And then finally in SD-RAM, I just use it for reads. And I use it for the bitmap ROMs and the program ROMs. So I'll show you now on the Analog Pocket what that same screen looks like. It's gonna be buggy, okay? I just got this to work like yesterday, okay? So bear with me. All right, let me, yeah, no, it's not straightforward. You can't just like run it. So you gotta reset it. No, well, yes. So what button? Oh, do I press it? You got it. All right, NARC. It's showing, right? Yeah. Yep. It's a little glitchy, so you have to bear with me. I just got this to work yesterday. There's some bugs that I have to work on. To get this to fit, I actually killed the GPU in the CPU. I had the GPU implemented. The GPU in the CPU is only used for the screens that show the board and the post check. They're not used anywhere else in the game. So I can I wrote a ROM patch to bypass that screen and go straight to the game. How do I do the menu? Is it the center button? I just have to do this because I don't have NVRAM saving yet. So I have to do that to show you this thing. So it'll go to the game now. It'll go to that screen, more specifically. But I just want to show you the speed at which it runs. So it runs really fast, right? If you notice. And that's about the speed that it should run on the board because I have all this in SRAM, right? SRAM is hyper fast. It's way faster than the SD-RAM that I had. So yeah, that's that. So that's how that screen works on the Pocket in comparison with the Mister. So with the Analog Pocket, I get more options in terms of the memory because of the memory architecture, and I use them to basically allocate the memory more efficiently and put things where the latency is low and I need it the most. So obviously I want to dedicate the highest power ones to the VRAM because you need to push pixels really fast. And you need to, the main RAM doesn't need to be so fast. And the CMOS RAM definitely does not need to be very fast. So I put that in pseudo-static RAM. But still PS RAM is about the same latency, I would say, as SD RAM. But again, main RAM is not something that's written to from a high bandwidth perspective, right? So I thought to put that in PS RAM. And then color RAM is definitely something you want to put in BRAM no matter what, because for every pixel that you push to the screen, you have to look up an entry in the color palette, right? So that's what the color RAM does. It's basically an index of all your colors and palettes, right? And and you convert that to the actual pixel that you're drawing on the screen. That needs to be hyper fast, right? Because it needs to push pixels to the screen on time every time. Like you can't stop it and do other things and wait for frames to push to the screen. That needs to be really fast. That should always be in BRAM. It should never be in anything else. It should be the lowest latency, highest speed, highest bandwidth thing that there should be. And bitmap RAM is also essential too, because bitmap RAM is basically, and you're either going to draw pixels from the CPU and push it to the memory, or you're going to basically use DMA, take it from the SD RAM, and push it to the RAMs. So you're either going to do one or two patterns with that, but that definitely needs to be very fast the way it is. Palette RAM is replicated, so for every pixel that you draw, you're drawing 2 pixels because you're writing 32 bits at a time, right? So 16 bits is 1 pixel. For every pixel that you draw, palette RAM is replicated across those 2 pixels. So how they achieved the high bandwidth that they needed on the real board is when they wrote 2 pixels, they would replicate the palette RAM part twice in 2 different addresses. And so that's how they achieved the high bandwidth, because you're really only doing one write, and you're replicating the same thing across to an adjacent memory address. And so that's how that worked, basically. So that's an overview of the work that was done in the Z unit. And hopefully I'm still going through validation. I'm still going through the validating the CPU and the core. So hopefully I'll be able to come up with something awesome. You can only hope in FPGA development. I mean, there's a lot of roadblocks. There's a lot of issues we need to debug, and it takes time to do them. So that's it.
We'd like to thank you all for attending our panel. Like he said, hopefully in a couple of weeks we have some good things to come. We'll see some output from NARC. Pramod here spent all night working on it, trying to debug a couple of little issues, and he figured out some stuff maybe about an hour and a half before we had to be here, and we just didn't have time to implement it. That flashing.
That's a work in progress, guys. Work in progress.
We know what the problem is now, but that's just the way it goes. I got very lucky and was able to set the priority in the palette for Twin Cobra before we showed up. I kind of wanted to have it done for this weekend, but I got that working, and then Flying Shark, there's the issues that I spoke about during the presentation there. They actually are a problem for Twin Cobra too. You don't see it in gameplay, but it's there, so I want to fix it before I release those next 2 Toaplan games. And And so that's pretty much our panel, and we'd like to thank you all for coming. And we've got some stuff planned this year, other than what we've been talking about. And we have Mars upcoming as well that we developed for. And I still have some things in store for Mister and the Pocket as well. And thank you all for attending.
Thank you very much, guys.